Let us start with electronic spectroscopy. Now, electronic spectroscopy deals with electrons. Okay, electrons present in a molecule. So, what are the different types of electrons that can be used in this technique? So, it is the valence electrons that are utilized. Okay, the valence electrons are utilized because the valence electrons, they can move about. Okay, the inner electrons, they are present inside the orbitals, deep inside the orbitals, and so they are not involved in bonding. Okay, and it is not possible for them to move about. But the valence electrons, that is the outermost electrons, they are involved in bonding, and not only that, they can move about. Okay, they can move about, they are mobile in nature. So valence electrons are present in molecular orbitals. So we are mainly dealing with organic compounds. So this technique is used to identify organic compounds. So in organic compounds, valence electrons, they are present in molecular orbitals. And these electrons can absorb a radiation and undergo a transition from one molecular orbital to another. Now you might have come across the molecular orbital theory in your lower classes. So atomic orbitals, when atoms combine to give molecules, the atomic orbitals, they will combine to give molecular orbitals. The molecular orbitals are arranged in the order of energy, and you can fill electrons into that. So when you fill the electrons, there will be some levels which are empty, there will be some which are filled. So from this filled level to the empty level, the electron can move. Okay. Now, which radiation is absorbed here? It is found that the radiation absorbed is in the UV visible region. Okay, UV visible region. And so, this technique is known by another name. Electronic spectroscopy is known by another name. And what is that name? The name is ultraviolet visible spectroscopy, or you can use the short form UV visible spectroscopy. Okay. Why it is called UV visible spectroscopy? Because the radiation absorbed is in the UV visible region. So this is one important question. Explain the principle behind electronic spectroscopy. Okay, this is an important question. You can note down this question. Explain the principle behind electronic spectroscopy. And another question, why is electronic spectroscopy called UV visible spectroscopy? So these are two important questions. Short answer type questions. Now let us look at the UV visible radiation. UV visible radiation, it is measured in terms of wavelength. Okay, wavelength, lambda. What is the wavelength of these radiations? Visible radiation, it is 400 to 750 nanometers. That is the wavelength range, 400 to 750 nanometers. UV region is divided into two parts. One part is called near UV region, that is 200 to 400 nanometers. The other part is called far UV region, that is 100 to 200 nanometers. Now far UV region, this radiation 100 to 200 nanometers, that can be observed only if there is vacuum, only in presence of a vacuum. So this region of the UV radiation is also called vacuum UV. Okay. Now because these radiations, that is Radiations in the wavelength range 100 to 200 nanometers will react with air. They will be absorbed by air. So if air is present, we cannot detect these radiations. Coming to the valence electrons and molecular orbitals, what are the different types of electrons present and what are the different types of molecular orbitals present? Now we know in organic compounds there are two types of bonds present. All are covalent bonds. In covalent bond itself there are two types of bonds. One is called the sigma bond and the other is called the pi bond. Okay, sigma bond and pi bond. So sigma bond will contain sigma electrons and pi bond will contain pi electrons. So these are the two types of electrons present. Now in addition to these two, you have some electrons like nitrogen. Nitrogen has a lone pair of electrons. Oxygen has two lone pairs of electrons. These are not directly involved in bonding, but these can be used for bonding if required. So these are classified as N, non-bonding electrons. Okay, non-bonding electrons or lone pair. You can call it lone pair, but in spectroscopy these are called as non-bonding electrons. Then what are the different molecular orbitals present? Now sigma bond means the molecular orbital will also be sigma. Sigma orbital. Sigma electrons can sit only in sigma orbitals and there are two types of sigma orbitals. One is the sigma and sigma star. Okay. Sigma and sigma star. Sigma is the bonding molecular orbital. This is the anti-bonding molecular orbital. So sigma electrons will be in sigma or sigma star orbital, that is bonding and anti-bonding. Then pi electrons, they will be sitting in the pi or pi bonding orbital or the pi star anti-bonding orbital. Then these n electrons, non-bonding electrons, they are in the non-bonding orbital. Okay, it's called non-bonding orbital. So these are the different types of orbitals present. Orbitals: sigma, sigma star, pi, pi star, and n, non-bonding. Electrons, you have sigma electrons, pi electrons, and the non-bonding n electrons. Let us draw the diagram for that. Okay, in terms of energy, let us draw the diagram. So molecular orbitals, they can be arranged in the order of energy, and when you arrange that, you will be getting something like this: sigma, pi, pi star, sigma star. These are the different levels. Okay, and you have the non-bonding. The non-bonding comes in between. Okay, non-bond. So these are the bonding orbitals. These are the anti-bonding orbitals. In between the bonding and the anti-bonding, you have the non-bonding orbital. So this is the energy level diagram for any organic compound. General energy level diagram for an organic compound. Let us consider the sigma orbital. Okay, in the sigma orbital you have sigma electrons. So when electrons are filled, they will be first filling in the bonding orbitals, and only when the bonding orbitals are completed, they will go to the anti-bonding orbital. So let us consider sigma electrons. Sigma electrons are sitting in the sigma orbital. They can absorb energy and they can move to any other orbital, but they cannot move to any as they like. They cannot move as they like. They can only move from sigma level to sigma star level. Okay, sigma level to sigma star level. Why? Because the symmetry of the orbital should be comparable. Only then the electron can move from one orbital to another. So sigma and sigma star have comparable symmetry. So the sigma electron will move from the sigma level to the sigma star level. Okay, sigma level to the sigma star level, and this is called sigma to sigma star transition. Sigma to sigma star transition. Now consider pi electrons. If pi electrons are present, where can they move? By absorbing energy. So the symmetry of pi and pi star are similar. So pi electrons will move from this level to pi star level. That is called pi to pi star transition. Pi to pi star transition. What about the n electrons? You have the n electrons, non-bonding electrons. Non-bonding electrons or non-bonding orbital does not have a fixed symmetry. Okay, does not have a fixed symmetry. So they can move to any orbital. From here, they can absorb energy, they can move to this one or they can move to this one. So you get two transitions like that. One is the n to sigma star transition and the other one is the n to pi star transition. So these are the electronic transitions present or possible in an organic compound. These are the electronic transitions possible in an electronic compound. Sigma to sigma star, pi to pi star, n to sigma star and n to pi star. These are the four electronic transitions possible in organic compounds. Now let us see one by one. One by one we can see in detail. Take down this question. This is an important question. What are the electronic transitions seen in organic compounds? What are the electronic transitions seen in organic compounds? Now let us see one by one. Sigma to sigma star transitions. The first one. So when you write that, you can write like this: sigma hyphen sigma star. So this means sigma to sigma star. This is shown by saturated hydrocarbons. Okay, saturated hydrocarbons. For example, methane, ethane, propane, butane, hexane, etc. These are saturated hydrocarbons. They contain only sigma bonds. Okay, methane, it contains only sigma bonds. Ethane, propane, they contain only sigma bonds. So they are called saturated hydrocarbons. They will give sigma to sigma star transitions. But there is a small problem here. These transitions occur in the far UV region. Okay, so if a sigma electron has to absorb a radiation and go to the sigma star orbital, then that radiation should be in the far UV region, less than 200 nanometers. Okay, less than 200 nanometers. But the issue here is instruments can measure only 200 and above. Okay, the instruments, normal spectrometers, can measure only 200 and above. So the problem is we cannot detect these transitions by normal instruments. Okay, normal UV, that is normal spectrometers cannot detect these transitions. If you want to detect them the spectrometers should have vacuum attached to it, and vacuum based spectrometers are very costly, so normally it cannot be afforded. So sigma to sigma star transitions, they are taking place, but they cannot be detected by normal spectrometers due to a technical difficulty. Okay, it is taking place, but it cannot be detected. So this is the sigma to sigma star transition. Pi to pi star transition. Okay, pi to pi star transition, it is shown by olefins or aromatic compounds. For example, now the essential condition here is there should be a carbon-carbon multiple bond. It can be double bond, it can be triple bond, but there should be a carbon-carbon multiple bond. Only compounds containing this bond will show pi to pi star transitions. For example, ethylene, propylene, butadiene, benzene. These are four compounds. Ethylene, propylene, butadiene, benzene. So these four compounds, they will show pi to pi star transitions. These transitions occur in the near UV region, 200 to 400 nanometer, so it can be detected by normal spectrometers. Next is N to sigma star transition. N to sigma star transition. It is shown by saturated hydrocarbons with heteroatom. For example, a compound containing carbon singly bonded to a heteroatom. Heteroatom can be oxygen, nitrogen, sulfur, or halogens. Oxygen, nitrogen, sulfur, or halogens. Okay. For example, ethyl chloride, ethyl alcohol, ethyl amine, all these contain heteroatoms, carbon singly bonded to heteroatoms. And these transitions also occur in the near UV region. Okay, near UV means 200 to 400 nanometer. The last one, N to pi star transitions. These are shown by multiple bonded heteroatoms. That is, carbon is multiply bonded to a heteroatom. Heteroatom can be oxygen, nitrogen, or sulfur. So compounds containing C double bond O, C triple bond N, etc. These compounds will show this transition. Example, acetaldehyde, acetone, methyl nitrile, phenol, aniline, etc. will show N to pi star transitions, and these transitions occur in the near UV region or visible region. Okay, sometimes these transitions will occur in the visible region also. So this question, let us look at this question. Which of the following molecules show N to pi star transitions? Give reasons. Now you are given four compounds. Okay, let us look at each. This is ethane. N to pi star transition means what is the essential condition? Condition is carbon multiply bonded to heteroatom, oxygen, nitrogen, sulfur, etc. So here there are no heteroatoms, here also there are no heteroatoms, so these two will not give. Here there is a heteroatom, but there is no multiple bond. It is CH3 single bond Cl. So this compound, it contains C double bond O. So this compound will give N to pi star transition. So this is the answer. CH3CH2 acetaldehyde will give N to pi star transition because it contains a multiple bond between carbon and heteroatom. Multiple bond between carbon and heteroatom. So this is one important question as far as your exam is concerned. Another question. What are the electronic transitions shown by the following compounds? You are given 4 compounds. You have to write what are the electronic transitions shown. Okay. So let us start with this one. Ethane. What are the electronic transitions? Ethane shows sigma to sigma star transition. Okay, only that. Then ethene. Ethene shows what all transitions. There are sigma bonds, there are pi bonds also. So it will show sigma to sigma star and pi to pi star transition. This compound CH3Cl, there is a sigma bond, there is a heteroatom. So since sigma bond is there, it will show sigma to sigma star transition. Since heteroatom is there, it will show N to sigma star transition. What about this last compound, CH3CHO? It shows all transitions. Sigma bonds are there, so sigma to sigma star transition. Pi bond is there, so pi to pi star transition. N, that is non-bonding heteroatom is there, so N to sigma star, and heteroatom is multiply bonded to carbon, so N to pi star transition. All transitions will be shown by this compound. So this is the answer to this question. Okay, so these are some important questions. Let us look at the energy level diagram of some molecules. Energy level diagram of a few molecules, important molecules. So energy level diagram means we have seen the general energy level diagram, that is sigma, pi, n, etc. For each molecule specifically we can draw the energy level diagram. For example, this is the energy level diagram for ethane. Ethane contains only sigma bonds. So you have the sigma electron, sigma orbital and the sigma star orbital. Sigma orbital, sigma star orbital. Sigma orbitals are full. Sigma star is empty. So this electron from here, it can absorb energy, it can go to this level. And the radiation absorbed is 150 nanometers. Okay, lambda max. I will tell you what lambda max is. Lambda max is the wavelength of maximum absorption. I will explain that later. But this molecule absorbs this radiation. We can just assume like that for now. This molecule absorbs this radiation, 150 nanometers, for sigma to sigma star transition. Now let us look at the next compound, ethylene. Ethylene, this is the molecular orbitals. Okay, sigma is there, pi is there, pi star, sigma star. So from this pi, the electron can absorb an energy, go to pi star. And the radiation absorbed is 180 nanometers. So earlier one, it was ethane. Ethane had a single bond. Now when the single bond was changed to double bond, you see the wavelength that is absorbed increases. Okay, the wavelength increases. Now what I'm going to do is I'm going to add one more ethylene to this compound. Okay, one more ethylene I am going to add here. So I will get a compound called butadiene. This is butadiene. Two ethylenes combined together. That is butadiene. Butadiene, if you look, these are the molecular orbitals. Sigma I have avoided because it is below. Okay, it is deep inside. So I have avoided that. These are the outer levels. So pi 1, there are two double bonds here. If there is one double bond, you have one pi and one pi star. But there are two double bonds here, so you have two pi's and two pi stars. So from here to here, the electron can move by absorbing a radiation, and the radiation absorbed is 217 nanometers. So earlier it was 180. Now it increased to 217. What has happened here? Number of double bonds has increased. Next compound, one more ethylene I am going to add to this end. Okay, if I add one more ethylene here, I will be getting hexatriene. This is the structure of hexatriene. So there are three double bonds. So 3 pi orbitals, 3 pi star orbitals, and this electron can absorb a radiation, go to this pi star level. The radiation absorbed is 248 nanometers. 248 nanometers. It has increased. Okay, double bond has increased, so the wavelength of the radiation absorbed has also increased. The last compound next. What I am going to do here, this hexatriene, I am going to make it cyclic. Okay, connect the first and the last carbon atom together, so it will become a cyclic compound. We get the cyclic compound benzene. Benzene. So in benzene, these are the orbitals, and benzene requires a radiation 255 nanometers. 255 nanometers. Okay, that has again increased. So as the number of double bonds increases, the wavelength of the radiation absorbed also increases. Okay, so these double bonds, they are called as conjugated double bonds. Okay, conjugated double bonds. Now you can note this question. Comment on the role of conjugation in the wavelength of absorption with the help of examples. Okay, so what is conjugation? The presence of conjugation means alternate single and double bonds. Like here you can see there is a double bond here, then a single bond, then a double bond. Here also double, single, double, single, double. So when you go like that, that is called conjugation. So as conjugation increases, the wavelength of absorption also increases. Okay, like ethylene, there is no conjugation, but there is a double bond, 180 nanometers. When you get one conjugation here, it becomes 217. When you get two conjugations, it becomes 248. Benzene has ring structure, so there is multiple conjugation, isn't it? You know, resonance takes place, so again the wavelength increases, it becomes 255. So this is an important question from your examination viewpoint. Comment on the role of conjugation in the wavelength of absorption with the help of examples. Now another question, which molecule will absorb at longest wavelength in UV? Explain. You are given two molecules, A and B. You have to find out which one will absorb longer wavelength. Okay. So how will you do that? So if there is conjugation, then that will absorb longer wavelength. As conjugation increases, the wavelength absorbed also increases. So you have to check in which molecule there is conjugation. Conjugation means what? Alternate single and double bond. You can see here there is a double bond, single bond, double bond. Okay, there is conjugation here. Here double bond, single bond, single bond, double bond. Okay, so there is no conjugation. Conjugation means one double bond, then one single bond, then one double bond, like that. Here there is no conjugation, but here there is conjugation. So molecule A will absorb the longest wavelength. Okay, molecule A will absorb the longest wavelength because of the presence of conjugated bonds. Now let us look at the applications of electronic spectroscopy. So electronic spectroscopy is applied for identification of organic compounds. This is the first application. So each organic compound has or will absorb a unique radiation. Okay, each organic compound absorbs a different radiation, and from that we can find out what is a compound. We can identify the organic compound. We can understand presence of conjugation or aromaticity. If the radiation absorbed, the wavelength of the radiation absorbed is higher, it means that there is conjugation or aromaticity in the compound. We can use this for quantitative analysis. How that is used, we will discuss that later. Okay, we will discuss in detail about that later. We can find out the band gap in semiconductors. This is one major application because a lot of semiconductors are used in several devices, isn't it? As OLED, as LEDs, then in chips, in modern chips and all, many semiconductors are used. So to find out the band gap of these semiconductors, we can use this technique. We can detect impurities present in a compound like benzene. Benzene absorbs a radiation of wavelength 255 nanometers. If there is an impurity, that impurity will be absorbing another radiation. So from that we can find out whether there is impurity or not. Finally, we can study the kinetics of a reaction using this technique. Okay, so each stage there will be a difference in the concentration. When a reaction proceeds, as time progresses, the concentration of the reactant decreases, the concentration of the product increases. So we can find it out using this technique. So these are some of the applications of electronic spectroscopy. How does the instrument work? That is what we are going to see next. The construction and working of the electronic spectroscopy instrument, and the instrument is called a UV visible spectrometer. This is a picture, a photograph of a UV visible spectrometer. Now this instrument costs around 3 to 5 lakhs. How does the instrument work? Now let us look at the block diagram of this instrument. This is a block diagram of a UV visible spectrometer. Now it starts here. Okay, so this is a source. Source means it is a light source, a source of radiation. So the light source produces UV visible radiations, and that passes through a slit. So you get a small beam, and you have what is known as a monochromator. Now the function of this monochromator is to convert all the radiations into a single wavelength. Okay, it will allow only a single wavelength to pass through. So you have a dispersion device. This is mostly a prism or a grating, diffraction grating, and that will split the radiations into different wavelengths, and using this exit slit only one wavelength is allowed to come out. This comes into a sample. Now the sample is placed in a holder. So that is something like a tube of this shape. It can be made of quartz. Normally when you are using UV radiations, it should be made of quartz. If you are using only visible radiation, you can use glass also, but glass will absorb UV radiation. So quartz is used. In this tube, the sample is taken. Sample is taken in the liquid form, and the radiation is allowed to fall. The radiation of a single wavelength is allowed to fall, pass through the sample, and it comes out. There is a detector. The detector detects the intensity of this radiation. It measures the intensity of this radiation. Now if you change this slit, the position of the slit, you can change the wavelength of this radiation. Okay, so that is how it is done. The light or the radiation that comes in is in the UV visible range, and using the monochromator we are splitting it into individual wavelengths, and then each wavelength is allowed to pass through the sample and the intensity is detected. So this is how the instrument is working. These are the different parts. Once again we can go through the requirements of that. There is a light source which produces radiations in the UV visible region with constant intensity. That is the important thing, constant intensity. And you have a monochromator which selects the radiation of a single wavelength. Now you can set that. Like if you set 250 nanometers, then only that radiation will be coming out. And you can vary that also. That is, you can set 200, then after change it to 201, change it to 202. Likewise, you can vary that also. That is a monochromator. Then you have a sample holder, which is a quartz tube which holds the sample. The sample is taken in the liquid state. And you have a detector and analyzer. It detects the radiation coming out and measures its intensity. And the result goes into a computer. The computer generates the final result in the form of a graph. Okay, so these are the basic requirements. So this important question, give the instrumentation of UV visible spectrometer and explain the components in it. Instrumentation means block diagram. You have to draw the diagram. Instrumentation means the block diagram of the instrument. Okay, and explain the components. You have to explain the different parts. What is light source, what is monochromator, what is sample holder, etc. Just one sentence explanation. Now how does this work? So you take a sample. Let us say you are taking benzene. You keep that in the sample tube, insert the sample tube in the sample holder, switch on the light source, so light will pass through this one, and adjust the monochromator or select the suitable wavelength. Like we will start with 200 nanometers and allow the light to pass through. It will reach the detector. Then you change the wavelength, change it to 201, 202, 203, etc., etc. So up to 750. Okay, so from 200 to 750, each wavelength is allowed to pass through the solution, and the detector detects the intensity of this radiation. And then a graph is plotted finally by the computer. So 200 to 800 nanometers we can vary. Now this is a sample graph, a UV visible spectrum for a compound rhodamine B. Okay. Now in the y-axis we have absorbance. I will explain that a little later. In the x-axis you have wavelength in nanometers. So you start from 200 up to 800. Okay. So for each wavelength, what is measured? The intensity of the radiation that comes out is measured. The initial intensity, that is the intensity of the radiation that goes into the sample, that is a constant. But the radiation coming out will differ because this molecule, this compound will be absorbing some radiation. So when it absorbs a radiation, in the spectrum we will get a peak like this. This is called as a peak. This is the structure of rhodamine B. This is called as a peak. Okay. So here the peak is appearing at 546 nanometers. It means that this radiation gets absorbed maximum by this compound. Okay. 546 nanometer radiation gets absorbed maximum by this compound. Now if you look at the structure, you can see there are several conjugated double bonds. There is nitrogen, oxygen, double bond oxygen, everything is there. So the absorption will be in the visible region. 546 nanometer means it is in the visible region. Okay, so this is a spectrum. What is this absorbance? Absorbance is the ratio of the intensity of light going inside and coming outside. That is initial intensity divided by final intensity. Okay, that is absorbance. I will explain that a little bit later. So this is the UV visible spectrum, sample UV visible spectrum. And this is known as a peak. Okay, something like a mountain. This is something like a mountain, and that mountain shaped figure, that is called as a peak. So you can see there is a peak, a small peak here, there is a small peak here, but this is a very large peak, the largest peak. The largest peak will be the lambda max, that is the wavelength absorbed by this compound. That will be the largest peak. It is found that in case of rhodamine B, this peak is due to the N to pi star transitions. Okay, N to pi, because there are many heteroatoms multiply bonded to carbon, everything is there. So this is the N to pi star transition. So this is a sample UV visible spectrum. Now let us look at what is absorbance. Okay, we have to see what is absorbance. So consider a sample holder. Okay, you have the sample in that. You are passing a monochromatic radiation of a single wavelength through that. Let us assume that this wavelength gets absorbed. Okay, it is the lambda max that you are passing that gets absorbed. So the absorption will be something like this. So you can see here the intensity of this light is continuously changing when it is inside the sample. Okay, initially intensity was this one, final intensity is this one. Inside you can see it is continuously changing. Okay, continuously changing. Now suppose that I0 is the initial intensity, I is the final intensity, L is the length traveled by light, distance traveled by light inside the sample. Okay, L is the distance traveled by light inside the sample, and C is the concentration of the sample. So I0 is the initial intensity, I is the final intensity, L is the distance traveled by the light inside the sample, and C is the concentration of the sample. So there is a relation, mathematical relation between these four parameters. What is that relation? This is a relation log I0 by I is equal to epsilon CL. Okay, log I0 by I is equal to epsilon CL. I will tell you what is epsilon. But log I0 by I, that is equal to A, and A is called the absorbance. Okay, A is called the absorbance. So we can write A is equal to epsilon CL. A is the absorbance. Epsilon is called molar absorptivity coefficient. L is the path length, and C is the concentration. This is known as the Beer-Lambert law. This is a very fundamental law in spectroscopy. Very fundamental law in spectroscopy. So A is equal to absorbance, epsilon is the molar absorptivity coefficient, and L is the path length, C is the concentration. So A is equal to log I0 by I, where I0 is the initial intensity of the light and I is the final intensity of light. So A is equal to epsilon CL, Beer-Lambert law. Now suppose you are plotting a graph between A and C using that equation. A is equal to epsilon CL. Using that equation, if you are plotting a graph, then you get several points like this, and if you join these points, you will be getting a straight line which passes through the origin. Okay, you get a straight line passing through the origin, and from that we can calculate the value of epsilon. How do we do that? The slope of this line is equal to epsilon L. Slope of this line is equal to epsilon L, and L will be a constant for an instrument. Generally it is 1 centimeter. So we substitute that value for L, we can find out what is the molar absorptivity coefficient. Okay, I will explain that in the next slide. The molar absorptivity coefficient. Now using the same thing, we can find out the concentration of an unknown concentration of a compound. Suppose you have a compound like potassium permanganate. So you prepare different solutions, different concentrations of potassium permanganate, find out the individual absorbance and plot this graph from that. Okay, you are given an unknown solution. You are given a solution of unknown concentration. You want to determine that concentration. So what you do? Find out the absorbance of that. Let that absorbance be A1. Okay, let the absorbance of the unknown concentration be A1. So from this point, draw a line touching this straight line, and from that point you draw a line downwards, vertically downwards. This value C1, that will be the concentration of the unknown solution, unknown concentration of the given solution. Okay, so this is how we can do quantitative analysis. In the applications of UV visible spectrometry or electronic spectroscopy, we saw that one application was quantitative analysis. So this is how we are doing quantitative analysis. Okay. Molar absorptivity coefficient is a constant for a particular substance. Okay. For a particular substance, it is a constant and it can be used for identifying different substances. Okay. So just like lambda max. Units of molar absorptivity coefficient. Molar absorptivity coefficient has two units. One is liter mole inverse centimeter inverse. The other is dm square, decimeter square mole inverse, and they are related by this expression. 1 liter mole inverse centimeter inverse is equal to 10 dm square mole inverse. So that is molar absorptivity coefficient epsilon. It is a constant. For a particular, like potassium permanganate, if you take, it has a fixed value. Okay, or if you take another compound like copper sulfate has another fixed value. So using that, we can identify what the substance is. When monochromatic light of different wavelengths pass through a solution, the absorbance obtained is different. Okay, the wavelength showing maximum absorbance is called lambda max. That is what we saw earlier. Lambda max we have seen earlier. So if you are allowing different wavelengths to pass through the same solution, then the absorbance shown by each wavelength will be different. But out of that, one wavelength will show maximum absorbance, and that wavelength is called lambda max. Each molecule has a unique lambda max. So just like epsilon, lambda max is also unique. So these two terms, that is epsilon and lambda max, can be used to identify compounds. First the lambda max is found out. Okay, first the lambda max is determined. If the lambda max are very close to each other, then we will find out what is the epsilon value. Epsilon value will definitely be different. Now this term I by I0, it is called T. We have seen log I0 by I is equal to A, isn't it? In that I by I0 can be written as T, where T is called the transmittance. Transmittance is the opposite of absorbance. So substituting that in the equation for absorbance, you get A is equal to log 1 by T, or A is equal to minus log T. This is an important expression. This is a very important expression. T ranges between 0 to 1. That is a range of T. A solution of concentration C1 gave an absorbance A1. Let us consider a solution of concentration C1. It gave an absorbance of A1. Another solution of the same substance of concentration C2 gave an absorbance A2 under similar conditions. Same substance you are taking, like what if you take potassium permanganate, one solution of concentration C1 gave an absorbance A1, another solution of potassium permanganate of concentration C2 gave absorbance A2 under similar conditions. So there is a relationship between these four parameters. A1, A2, C1 and C2 are related. So A1 is equal to epsilon C1L. Here epsilon and L are constant because the compound is the same. Again A2 is equal to epsilon C2L. Divide both. You get A1 by A2 is equal to C1 by C2. So this is another important expression in Beer-Lambert law. So the first expression was A is equal to epsilon CL. Then you have A is equal to minus log T. And then you have A1 by A2 is equal to C1 by C2. So these are the important expressions for Beer-Lambert law. Now coming to the limitations. What are the limitations of this law? It is not a universal law. It's a fundamental law, okay, but it is not a universal law. It cannot be applied under all conditions. Obeyed by dilute solutions only. The concentration increases, then what happens? It will not obey Beer-Lambert law. Concentration will not be proportional to absorbance, or absorbance will not be proportional to concentration. Okay. Then impurities lead to deviation. If there are impurities present in the compound, then the absorbance will not be equal to the concentration, will not be proportional to the concentration. Not obeyed by suspensions. Suspension means what? It's a colloidal solution, or it is not fully dissolved, isn't it? So such compounds, when light passes through them, the light gets scattered away. So it will not be absorbed properly. We want the absorption. So it will not be absorbed properly. Then only monochromatic radiation can be used. You cannot use white light. Okay, you cannot use white light because white light is a mixture of different radiations, and when that passes through a solution, Beer-Lambert law is not obeyed. So you need monochromatic radiation only. Not obeyed by fluorescent materials. Yes, fluorescent materials, they will emit light of their own. So such materials, they will not absorb the light properly. Operating conditions may cause deviation. Like for example, if there is a voltage fluctuation, then the value will be different. Okay. And finally, the structure of the molecule should not change during the measurement. For example, if you take potassium dichromate, dichromate ion is orange colored. But when you make a solution, when you dissolve dichromate in water, it can hydrolyze and it can give chromate. This is chromate. Chromate has a yellow color. Okay, so if you are measuring the absorbance of this one, its structure has changed to this one. Part of it might have changed to this one. So you will not get the correct absorbance, or you cannot relate absorbance with the concentration. So structure of the molecule should not change during the observation. So these are some of the limitations of Beer-Lambert law. So these are the three important equations, mathematical equations. A is equal to epsilon Cl, A is equal to minus log T, and A1 by A2 is equal to C1 by C2. We have to do some numerical problems based on these three equations. Okay, so we can see some examples, some numerical problems. This is the first question. Calculate the molar absorptivity of a 0.5 into 10 raised to minus 3 molar dye solution in ethanol, which shows an absorbance of 0.17 when 1.3 centimeter cell is used. This is the question. So what you have to do, calculate the molar absorptivity. Molar absorptivity means the molar absorptivity coefficient epsilon. You have to calculate that. Of a 0.5 to 10 raised to minus 3 molar dye solution. So concentration C is given, which shows an absorbance of 0.17. So A is given when 1.3 centimeter cell is used. So L is also given. A is equal to epsilon Cl. We have to calculate epsilon. A is given 0.17, C is 0.5 to 10 raised to minus 3 molar, and L is equal to 1.3 centimeter. Direct substitution. So what will be epsilon from this equation? If you rearrange this expression, you get epsilon is equal to A by Cl. Substitute the values. A is 0.17, C is this one, L is this one. Substitute that. Substitution and calculation finally will give you this result. Epsilon is equal to 261.54 liter mole inverse centimeter inverse. How did you get this? This one, liter mole inverse centimeter inverse. How did you get? Concentration is molar. Molar means moles per liter. Length is centimeter. So A, absorbance, it is unitless, no unit for absorbance. Substituting that value, you will get this unit, liter mole inverse centimeter inverse. So this is how you do this question. It's a very simple direct substitution. Next question. A solution of concentration 1.25 into 10 raised to minus 4 molar was analyzed in a cell of 1.5 centimeter thickness. Calculate its absorbance if the molar absorption coefficient is 29460 dm square mole inverse. Same formula, but we have to calculate the absorbance. The other terms are given. So epsilon is given, molar absorption coefficient 29460 dm square mole inverse, that is given. Concentration is given 1.25 to 10 raised to minus 4 molar, that you can write as 1.25 into 10 raised to minus 4 mole per liter. Molar means mole per liter. And path length L, that is given 1.5 centimeter. What is the formula that you can use? So here, this is a conversion factor. Now you have this in dm square mole inverse. This is mole per liter. This is in centimeter. Okay, so the units are not matching. So what you have to do? This you have to convert to liter mole inverse centimeter inverse. Okay, dm square mole inverse you have to convert into liter mole inverse centimeter inverse. Then all the units will get cancelled and you will get the final answer. So this is a conversion factor. 1 liter mole inverse centimeter inverse is equal to 10 dm square mole inverse. So what will be this value? 29460 dm square mole inverse. That will be equal to 2946 liter mole inverse centimeter. So you got all the factors. Epsilon you got, C you got, L you got. Now substitute. A is equal to epsilon Cl. Direct substitution. So when you substitute, you get like this 0.5524. This is the answer. Absorbance of the solution is 0.5524. Now what do you mean by absorbance is 0.5524? It means that 55.24% of that radiation is absorbed. Okay, 55.24% of that radiation is absorbed. Next question. A 0.01 molar ferric thiocyanate solution showed an absorbance of 0.463 when measured using a cell of path length 1 cm at a wavelength of 480 nanometers. Another solution of the same substance showed an absorbance of 0.844 when measured under similar conditions. Determine the concentration of the second solution. This is the question. So what is given here? 0.01 molar ferric thiocyanate solution showed an absorbance of 0.463. So this is the formula that you are going to use. A1 by A2 is equal to C1 by C2. What is C1 here? So C1 is 0.01 molar. A1 is 0.463, that is given. Path length and wavelength, these are not required in this calculation. You can just avoid that. Then A2 is 0.844. From this we have to find out C2. C2 we have to find out. So how will you find out C2? Rearrange that equation. You get C2 is equal to A2 by A1 into C1. Substitute for A2, A1 and C1 and calculate. This is the result that you will be getting. 0.0182 molar. 0.0182 molar. So this is a direct substitution. And rearrange. Okay. A1 by A2 is equal to C1 by C2. Directly you are substituting that. The next question. A solution of concentration 0.024 molar showed a transmittance of 82% when measured in a cell of thickness 1.2 centimeter at a wavelength of 532 nanometers. Another solution of the same substance showed a transmittance of 36% when measured under similar conditions. Find the concentration of the second solution. Similar problem to the earlier one, only thing is instead of absorbance, transmittance is given, and that too transmittance is given in percentage, not in whole number. Okay, this percentage that is. So same formula, A1 by A2 is equal to C1 by C2. Here C1 is given. A1 and A2 are not given. The transmittance is given, so we have to convert transmittance to absorbance. How is that done? A is equal to minus log T. You have to substitute in this equation, find out A1 and A2 and then you put it here. A1 is minus log T1, A2 is minus log T2. What is T1 and what is T2? Now T1 and T2, if you remember, the value of T should be between 0 and 1. Here it is given percentage. So you have to convert percentage into a value between 0 and 1. So what will be T1? T1 is equal to 82%. that you can write as 82 by 100, 82 out of 100 or 0.82. Then T2 is 36 percentage, that is 36 by 100, 0.36. So T1 is 0.82, T2 is 0.36. Substituting that value, here C1 is 0.24, then substituting the value, you will get C2 is A2 by A1 into C1, that is minus log T2 by minus log T1 into C1. Substitute the values, you get like this, and once you calculate, you will get the final answer 0.1235 molar. 0.1235 molar. So these are the different types of numerical problems that can be asked for your exam.